Okay, so today I'll be talking about hypervisor redundancy analysis, and here we are going to be doing a thorough discussion on how hypervisors can be protected from faults and improve their fault tolerance techniques. So we begin with the why we would need hypervisors in the present scenario, as all the hardware infrastructure that's traditionally the servers and all of that is moving to cloud. So more data centers are being used. So we have an exascale computing infrastructure wherein several thousands of servers are being linked to each other. So when this happens, the probability of fault occurrences also increases, and thereby we have parameters such as performance and cost and expense and all of the resource utilization parameters that we have to take into account, and we look at how we can optimize that and make best use of it. And we look at how to efficiently um, conduct our research and look for loopholes, security loopholes, vulnerabilities, and we also discuss the various mechanisms such as um, data replication, memory backups, and failure and recovery mechanisms, and of course the security and vulnerability assessment. So we can start by looking at what a hypervisor is and how it conducts its operations on a typical hardware system. So it's basically a software abstraction layer that is installed right over the kernel of the system. So we have the hardware in which we have the input, output ports, and the disk storage, and the memory access, and all of that. So right over the hardware layer, we have the abstraction layer, and this is basically the hypervisor. So hypervisor is basically it consists of a scheduler, so it schedules tasks, handles execution threads, and maintains a control flow. And this acts as the interface between virtual machines that we want to run with our underlying host machine, right? So, and most of our research topics basically here that deal with redundancy and fault tolerance um, lie in the domain 0, which is present in the left-hand side of the block diagram. So domain 0 handles, it acts as an interface between the hypervisor and all of the virtual machine applications that we'd like to run. So here we look at the examples of the leading industrial organizations that work in the virtualization technology. We have the VMware, ESXi, VMware's vSphere as the leading products. And we have Microsoft developing their Hyper-V and Citrix, which predominantly works with data storage and virtualization tools. So on the right-hand side, you see the diagram, which shows is a perfect example of optimization and optimal resource utilization, wherein the ESXi host developed by VMware does not have to rely on underlying hardware for 1 out of 3 hosts. So this cuts down the utilization by about 30%. And then we look at redundancy mechanisms and how we can overcome the faults to maintain redundancy. And dual visor is one of the novel techniques developed on the software level, wherein it replicates the execution threads and creates backups of these into a temporary memory, and it synchronizes this into runtime when the underlying host hypervisor runs into a fault or crashes into an error zone. So when that happens, the replicated hypervisor execution comes back into play, and it's synchronized back into the host hypervisor and restores the state. So just look at the pros and cons of dual visors. The performance overhead is very low. It's robust against software errors, but we inevitably cannot overcome hardware errors because that's the abstraction is only on the level of software, but it's not on hardware. And we can selectively replicate. It's been successful so far, but the loophole remains to be seen that the hardware replication is still at fault. So it supports spatial redundancy, but it's not suitable for high workload. So we may not achieve high spatial redundancy, but temporal redundancy is taken care of. So the next methodology is the is the fault tolerance Zen. FT-Zen has been developed as a modified software to virtually map virtual machines selectively from the hypervisor. So it doesn't have the interference overhead of several virtual machines coming into play and creating deadlocks. So we see the crash analysis by using FT-Zen when we implement this model in the next slide. So we see that the most commonly occurring hardware fault is that of a deadlock. So deadlock happens when there are several virtual machines interacting when there's a transmission of execution threads happening. So FTZen basically eliminates that, and it also eliminates other dominant faults such as page faults and fatal traps. We see that FTZen prevents deadlocks because of the lack of interference from several virtual machines transmitting and connected to the hypervisor itself. And then we have the page table fault handler. So this prevents any page faults or fatal traps, as we'd seen earlier. And it prevents the hypervisor from entering a panic mode. So in case there's a fault or an error that the hypervisor runs into, it doesn't have to enter a panic mode when it has to reboot or restart. So then we also isolate the global and local data structure so that the memory remains healthy. And it also works predominantly in domain 0. So this is the domain in which it has direct interaction with the underlying hardware. Next, we move on to performance aspects, and this is an experiment conducted on two identical servers which have the same technical configurations, and one of them runs a Citrix Zen server modification, and the other one runs the default latest KVM module. So when run, they use the nQueen's algorithm, which is a unique way to map several virtual CPU cores, which assuming its default as 24, and they're optimally utilized by all virtual machines so that there's no wastage of resource. So thereby this increases the performance aspect. Next, we look at the failure and recovery mechanisms, and the primary key component of this is checkpointing. So checkpointing is basically just a link between the primary host and the backup host that we want to back up our data into. So checkpoint acts as a runtime semaphore wherein the primary host creates some data and the backup host, is kept on pause. So once the checkpoint passes through and all of the data entries that have been made for the primary host, they pass on to the backup host. So this way, there is no synchronization faults, or say there is no backup being lost. There's no overhead of creating constant backups for the primary host. Next, we look at security aspects in brief. The research areas had been in Hypersafe, and Hypersafe is a software module to just maintain the control flow integrity. So as seen on the bottom right diagram, we see the flow going from there's a comparison between the benign state and the malicious state. So in traditional page table updates, we see that in malicious state, it just passes through without any checks or verification. But on using Hypersafe, we see that on malicious interaction with the page table entry, it blocks it off right there and it eliminates any risk of any malicious attack. And next we look at naive-based classifier. So this is basically based off of machine learning algorithm. So it gets in data, feeds in weights of parameters, various parameters of attack vectors, and from authentication point of view and confidential impact. So we give weights to each of these parameters, and depending on whether it's going to be an attack or not. So this works as an efficient prediction algorithm. So next key topic is high availability and disaster tolerance. This is key in any infrastructure as a service or cloud service providers. And the research was conducted with the experiment on the KMU KVM hypervisor. So this is basically a modified hypervisor platform that has been used to undergo the decision tree algorithm to allocate resources very well. And as you can see, the cloud manager, as it's traditionally called, is the is called the HA Cloud Controller. So this basically takes in the REST APIs from all the web applications in our cloud, and it distributes it to the node controllers in each data center, and it allocates the hypervisor accordingly. So there is optimum resource utilization without any wastage of any of the hypervisors. So thereby it uses everything. Finally, I discuss in brief the advantages containerization has over traditional virtual machines and use of hypervisors as a whole. So how virtual machines have to rely on underlying hardware at the end of the day, and they're always prone to hardware faults and kernel configuration faults or errors such as those. Whereas containerization works on the software layer, so it does not have any interaction with the underlying hardware whatsoever. So we can create several abstraction layers, replications, and migrate these containers or container images or snapshots, or as we colloquially call them, to various data centers.